All right, guys, I want to go over with you the answers to the review questions from section 4.1 that we assigned yesterday. In the process of that and answering the third question, we're also going to go over terminal velocity. Slide our board up in here. There we go. So, essentially here, for our first question, we have a weightlifter who raised a 440 kilogram barbell with an acceleration of 2 meters per second. How much force does the weightlifter exert on the barbell? So again, writing down our info, mass is 440 kilograms, acceleration is 2 meters per second squared. We're trying to find the force. The equation we're using is F equals ma. We're taking 440 kilograms times 2 meters per second squared, which should give us a force of 880 kilogram meters per second squared. Or remember, we said yesterday, a kilogram meter per second squared is equivalent to a Newton. So you could use 800 Newtons as your answer to that problem. The second one is very good. You didn't have to go through the process that I did, but I wanted to go through it and explain this to you. So the softball is larger and more massive than a baseball. Using Newton's second law, explain why players can't throw or hit a softball as far as a baseball. So I actually went and found some information. The mass of a baseball is 0.145 kilograms. The mass of, I believe, an 11-inch softball is 0.200 kilograms. The average swing, the average force in a swing of a baseball player is about 18,000 newtons. I didn't know that. I had to look that up. So using Newton's second law of motion, F equals ma, if you put 18,000 newtons of force, a mass of 0.145 kilograms to the baseball, you find the acceleration to be 124,137 meters per second squared. Whereas using the same formula and the same process with the mass of a softball, you end up with an acceleration of 90,000 meters per second squared. So obviously, the greater the mass, the less it's going to be able to accelerate. It's like, throwing a heavy object versus throwing a lighter object. The lighter object is going to go further. This is just the physics behind it. Final part for today. Looking at terminal velocity, this answers the third question. How can someone jump out of an airplane and end up falling safely to the ground? And this deals with what we've been talking about for the last few days. So again, if you guys don't remember from when we were back in school, my artistic ability is minimal, so we're going to use stick figures here. We have a stick figure jumping out of an airplane. Now the force of gravity, and these numbers are averages, numbers that I just kind of made up for this process, so you can see I use obviously whole round numbers, so it'd be easy to see the differences. But the force of gravity, we're going to say is about 800 newtons. Again, that's dependent upon the person's mass as they're falling here. The air resistance is 500 newtons going up in the opposite direction. So we have 800, the force of gravity is 800 newtons downward. The air resistance is 500 newtons up, which gives us a net force of 300 newtons down, which means you're going to accelerate down. The person is going to accelerate and fall faster and faster and faster. If you remember, we said yesterday, what are the factors that affect air resistance? Well, one of them is velocity. When you drive faster down the road and put your hand out, it's going to get blown back more. So the greater the velocity, the greater the air resistance. So the force of gravity is not going to change. The mass of the earth isn't changing. Your mass isn't changing as you're falling. So the force of gravity is going to remain 800 newtons. However, because the velocity increased, the force of air resistance is also going to increase. We're going to say it gets up to 800 newtons now. Well, at this point, the net force would be 0, which means you have no acceleration. When this happens, you have reached what we call terminal velocity. You're not going to get any faster. You're just going to continue falling at that speed. Unfortunately, though, that speed is way too fast to safely land on the ground. So we pull the ripcord and deploy our parachute. When we deploy the parachute, we greatly increase the air resistance. That's the surface area. Remember we said yesterday, small surface area, not much air resistance. When you turn your hand this way in the wind, we increase the surface area and thereby increase the air resistance. So now we've increased the air resistance to, let's say, 1,100 newtons. Gravity is still 800 newtons. The net force is now 300 newtons, going up, going opposite of motion. So the net force is 300 newtons opposite motion. Acceleration is opposite motion, which means you are decelerating or slowing down. That's the whole purpose of the parachute. As you are falling, as the velocity decreases, the air resistance will also decrease until we get to the point of an air resistance of 800 newtons again. Gravity is still 800 newtons. At this point, we have a zero net force, we have zero acceleration, we have again reached a terminal velocity. Although the terminal velocity with the parachute is a much smaller velocity than the free-falling velocity, so you can land safely on the ground. So hopefully that helps explain things to you guys. Have a good evening. Log on to tomorrow's assignment and warm-up question to continue moving through chapter 4.